Decreasing carbon footprint is a key step in taking action on the climate change problematic as to reducing CO2 emissions. Taking energy crisis into account, transforming CO2 into value-added produce through sustainable ways is the focus of a variety of studies involving numerous approaches. In this case, CO2 reduction is a reaction with slow kinetics and, thermodynamically unfavored, as in this case for photoelectrochemical CO2 reduction, high overpotential requirements are needed, and there are difficulty of separation of reaction products as well. Therefore, the challenge to transform CO2 into value-added products is placed and is taken into account with this study. Therefore, as a photocathode, a photoelectrochemically active material is needed, which shows aqueous stability, which shows obviously light absorption, and is also thermodynamically stable and capable of meeting the required potentials for CO2 reduction. Strontium titanate was chosen, however, it has shown poor CO2 absorption and also a large band gap, which is directly related to difficulty of charge separation. In order to tackle these other issues, graphite carbonitride was chosen as a means to enhance charge separation, narrow the band gap, and also amplify the light absorption spectrum. In order to synthesize the graphite carbonitride with strontium titanate, hydrothermal synthesis was done, parting from both precursors. 20% graphite carbonitride was placed with strontium titanate, and following hydrothermal synthesis, the reaction was performed. However, also a second composite was obtained through the same process, with only a difference that it was lastly calcined at 520 degrees Celsius in order to compare possible improved crystallinity. As for some materials, with calcination comes enhancement of crystallinity. After this, the hybrid, the precursors and both hybrid structures were deposited onto ITO via a spin coating process, and following this characterization, photoelectrochemical performance studies were performed. The microfluidic cell design was fabricated, and all of this aimed into successfully reducing CO2 via a microfluidic photoelectrochemical system. The results first showed that it was the materials were successfully deposited into the ITO via spin coating and after annealing in order to enhance the electrical contact of the materials with the ITO. These substrates were adequate for testing. As we can see in the first image, the ITO photocathodes were successfully prepared and are shown. Titanium oxide photocathode has multiple substrate exposed sections due to quick precipitation and the suspension. However, carbon nitride is the most uniform, whereas strontium titanate is the less uniform. In this case, we can observe that the graphite carbonitride strontium titanate nanocomposite, non-calcined, has an adequate surface which shows synergy between carbon nitride and strontium titanate, and whereas the calcined composite shows its appearance shows more resemblance with the titanium oxide. After this, a variety of characterization methods follow into validating the synthesis and some of the characteristics of the nanocomposite, such as light absorption. In this poster, we're showing the Raman spectra of the precursors and as well as of the calcined composites. Strontium titanate shows discernible peaks according to literature, which are shown in the spectra. Thus, naked eye comparison can be performed. And the first two amphor carbon nitride, also there are peaks which can be easily compared with the composite. In this case, the non-calcined composite showed no sign of graphitic carbon nitride Raman peaks, and also in other characterization methods such as FTIR, the signals were nowhere to be found. So graphitic carbon nitride, strontium titanate nanocomposite, calcined synthesis was deemed unsuccessful. However, the non-calcined composite synthesis was deemed successful. After this, other characterization methods followed. In this case, we can see the reflectance spectra of UVVs after its transformation via the Kovalka-Monk method in order to extrapolate and obtain the band gaps of all of the materials. In this case, we can obtain the band gaps in order to observe light absorption characteristics, and also as a means to compare these light absorption characteristics with those reported in literature. The obtained values are very close to those reported in literature, so this is also a good sign that the composite synthesis has the right composition, structure, and light absorption characteristics that were sought. After this, photoelectrochemical performance followed using a solar simulator, which worked at spectra of AM 1.5 G with an intensity of 1.1 suns, and the ITO photocathodes were placed in a 3-electrode configuration using potassium chloride 0.1 molar as its electrolyte. So using a potentiostat, we were able to evaluate all of these characteristics, such as cyclic voltammetry, linear sweep voltammetry, open circuit voltammetry, and also chronamperometries, and also impedance spectroscopy. In this case, we're showing the open circuit voltammetries with interrupted, first no light irradiation, then irradiated by light in order to observe its photovoltage, and after that the light was turned off in order to observe charge recombination and stability of the photovoltage. In this case, the photovoltage value was negative, which shows which is a great sign, as we were seeking an n-type photocathode, and this shows that charge separation is biased towards a more negative potential, which is desired for reduction processes. Also, we can observe the chronamperometry, and with no light, with interrupted light irradiation in order to observe electrical current and photoelectrical current. In this case, we can observe that the composite shows great photocurrent stability, shows a high value of photocurrent, and well, is the highest along with its precursor of strontium titanate, which is desired for the microfluidic CO2 reduction process. Now, in this case, well, after this, also I mentioned impedance spectroscopy. Impedance spectroscopy was used as a means to observe charge transfer resistance and to obtain the flat band potential via Mott-Schottky analysis. Following the flat band potential and adding the band gap obtained via UV-vis reflectance spectroscopy, the band alignments of the precursors and of the hybrid composite were obtained, and as we can see, the composite shows a shift towards more negative potentials, and the reduction potentials for CO2 reduction are met. So this means that the hybrid composite photocathode shows adequate photoelectrochemical activity for CO2 reduction. Finally, the microfluidic device was designed. Why was a microfluidic device designed? Well, it is important to remember that, as in any cell or reactor assembly, factors such as flow or transport effects can go unnoticed and heavily impact reactions, in this case photoelectrochemical catalysis. However, in order to solve this problem and to in order to solve low surface area to volume ratio, poor mass and photon transfer problems, the microfluidic device was proposed. This was fabricated first via CNC machining, and after that with 3D printing. And after a variety of proposed designs, a final design was deemed successful as and adequate enough for microfluidic CO2 reduction. This microfluidic CO2 continuous flow reactor is shown in this poster, and as it can be seen, well, it measures 5.1 centimeters per 2 centimeters per 1.68 centimeters, and it has a 102.50 microliter capacity. And using a microfluidic calculator, laminar flow was ensured. Also, this design was deemed adequate enough after, well, it showed no leaks, the electrical contact was isolated, flow rate was ensured, and it has it showed adequate performance using the potassium chloride 0.1 molar electrolyte. In conclusion, the composite via hydrothermal synthesis proved successful with the preliminary photoelectrochemical performance, and via the characterization methods, its synthesis was deemed successful. However, its calcined counterpart was deemed unsuccessful, as it showed no sign of graphitic carbon nitride concentration, well, of